Hi everyone, this is Team RoboErectus, and this is our team presentation video for the 2024 CoSpace Rescue University competition held in Qingdao, China. My name is 𝗣𝗏𝑨𝑷, and I'm here representing our team, myself, Darren, Qingdao, and Nicholas. Together, we participated in the RoboCup competition in Singapore in the Vision, Rescue, and ADO division. As part of our curriculum in school, we have worked on projects that require AI algorithms and programming, and this will be our first time competing in an overseas competition, the RCAP Qingdao 2024 for CoSpace Rescue University. For executive summary, our overall challenge was to accumulate the highest number of points and secure first place in the competition using a combination of techniques. To achieve this, we developed a multi-objective optimization algorithm capable of handling various tasks in a prioritized manner. Some of the key priorities we set include heading to the deposit when possible, maximizing point through object collection combinations, and finding the optimal method to journey the map. In the game, we used QR codes as QR codes were assigned to traps and deposit zones, with each code helping to differentiate between these areas. QR codes. In the game, QR codes are assigned to traps and deposit zones, with each code helping to differentiate between these areas. To begin, we have to decode the QR code. We convert the QR code into ones and zeros, with ones representing white and zeros representing black. We then combine the 6 ones and zeros of each line to create a binary string. The 6 binary strings represent the QR code. After that, we convert these binary strings into a hex code and add it into the robot's source code for it to be able to understand and decode these QR codes. How do we use QR codes? We can use the QR codes for the blue team to help us to deposit. First off, we have to find the 4 corners of the QR code. Using the x coordinates of these QR codes, we can then calculate the average coordinate of the QR code in the center. Using these coordinates, we can then calculate whether to turn left or turn right in order to position this QR code in the middle of the camera screen. Doing this will allow us to drive the robot straight into the QR code and let us deposit. Object collection. For object collection, the robot defined HSL color ranges for objects of interest, OOIs. It used a function we call arrange order to check the blobs against the OOI colors and prioritize these objects based on their proximity, also known as Y value. This is done by finding the lowest Y coordinate of the closest blob. Since the robot's color sensors N are set to the left and right of the center, if we just drive straight into the blob, the color sensor will just barely miss the blob and fail the collection. To prevent this, we have to calculate the x-coordinate offset for the camera to turn and align itself with the object and proceed with the collection. This ensures that the robot moves accurately and positions its RGB sensor over the object for precise collection, making the process more efficient. This shows how the robot would use the x-offset coordinate to turn and reach the object in one swift motion. Object combinations. Here we can see a graph on how much each item is worth, with Super and Super Plus objects being worth the most at 180 and 360 points respectively. These points count as the collection and deposit points combined. Object collection strategy. In the first run, our collection strategy focused on collecting the special combination of objects, particularly 2 red, 2 cyan, and 2 black objects. In subsequent rounds, if the Super Plus object is detected in the midst of the special combination collection, the robot prioritizes collecting the super object and changes its strategy to only collect 1 red, 1 green, and 1 black object. However, in the case that no Super Plus object is detected, the strategy stays and the robot carries on with the special combination collection. As depositing was the most challenging part of scoring points, we prioritized scoring by depositing whenever we had either the RGB combination and a super object or a special combination. Color tag reading. We also utilized color tags found on the walls during the game. These tags were used by the robot as reference points, helping it locate the deposit zones more efficiently. By recognizing these patterns, the robot was able to adjust its orientation and navigate more precisely to areas with deposit zones. Color tag usage. Firstly, we identified each color tag in the map. Then we assigned different numbers for each color in the color tags to be able to differentiate each color tag. This allowed us to instruct the robot to execute specific actions when a matching tag was detected. Finally, once the robot identified the color tags, it moved towards the tag and used ultrasound sensors to stop 70 units away from the marker before executing a turning function towards the deposit zone. After successfully depositing, the robot continued to collect more objects and performed subsequent tasks. This strategic approach to object detection, navigation, and collection allowed our robot to perform efficiently during deposits. Movement optimization. While moving in straight lines is effective, it can be further optimized by introducing a snake-like movement pattern. In this approach, the robot moves slightly to the left, then slightly to the right, repeating this cycle as it moves forward. This enhances its performance in several ways. Firstly, the robot's camera covers a wider area, improving its ability to detect and collect objects. Since it captures more of its surroundings, it has a higher chance of locating critical markers, like the deposit zone QR codes. This movement strategy ultimately makes the robot more efficient in navigating using QR codes and completing its tasks. Issues overcome. Firstly, version errors. The code we initially received was designed for an older version of CoSpace, which required us to make several modifications to ensure compatibility and improve its functionality. One of the primary changes we made involved increasing the array sizes for two key arrays, found blobs and array list. We expanded their sizes to be 10 times larger to address memory errors that were causing issues during runtime. Additionally, we had to adapt the onTimer function from the 2023 version of the program to work with the 2024 version, which required converting it into the AI loop and AI loop start functions. These adjustments allowed the program to run smoothly on the updated platform. Secondly, the robot faced two major issues when entering traps. First, the thinner yellow boundary on the new map led to delayed detection, causing the robot to enter the trap before recognizing the yellow boundary, which rendered the previous strategy of turning away ineffective, as it would hit the trap and lose all its objects. Second, the robot struggled to detect QR codes at diagonal angles, increasing the likelihood of entering traps before turning. To tackle these problems, we updated the code to integrate hex codes read by the camera from all four sides of the QR code, enabling detection from multiple angles and improving the robot's ability to recognize yellow boundaries sooner. However, a new issue arose with image clarity for the QR codes, resulting in gray pixels that distorted the appearance of the traps. The algorithm converts images of April text to black and white based on a predetermined color threshold, which can misclassify these gray pixels. We added code to adjust this threshold when the QR code appears blurry, enhancing the robot's ability to detect it accurately. In the first run, the robot aims to collect the special combination to produce a superplus object. In subsequent rounds during collection, if it detects the superplus objects, it makes space for it in its inventory and prioritizes the rest of its inventory for collecting an RGB combination. However, if the robot doesn't detect or collect the superplus object, it reverts its strategy to prioritize the special combination, generating a new superplus object upon deposit. Results. Our robot has become more dependable in locating and collecting objects, and its ability to generate and collect superplus objects has improved significantly. As a result, the robot's average score increased from 2.5 to 3.2K, reflecting a notable improvement in performance. While we are satisfied with these results, we believe that further improvements can still be made. By refining the algorithm and exploring new strategies, we can enhance the robot's efficiency even more and achieve better outcomes in future competitions. Real-world application. How can this be used in the real world? One use case is a real-world rescue operation. A robot equipped with computer vision can be a game changer by navigating through complex and dangerous environments while identifying crucial elements like survivors, hazards, or obstacles. In disaster areas, these robots can quickly assess unsafe zones, locate individuals trapped under debris, and recognize obstructions without requiring human intervention. This application greatly enhances the speed and safety of recovery missions, reducing risks for rescuers and improving the overall efficiency of search and rescue efforts. Future work. To further improve blob recognition, we plan to implement a convolutional neural network, or CNN. CNNs are excellent at learning spatial hierarchies of features, which will help the robot detect patterns more effectively. One key advantage of CNNs is that they require less training data than other types of neural networks, allowing us to deploy the system more quickly. By using CNNs, we aim to significantly enhance the robot's accuracy in object detection and overall performance. For AI tools, we use ChatGPT extensively throughout our project, both for brainstorming innovative solutions to complex problems and for providing valuable assistance with programming tasks. It played a crucial role in refining our approach, offering suggestions for optimizing code and helping us troubleshoot challenges along the way. By leveraging AI, we were able to enhance our problem-solving capabilities and streamline the development process. In conclusion, our approach combined advanced algorithms and practical strategies to optimize our robot's performance in the RoboCup competition. We are proud of our results and are excited about the potential improvements for future competitions. Thank you for your attention.